Welcome back, guys. So let's continue. How can I find the equation of acceleration in a curvilinear motion using the normal and tangential directions? So as I said before in the previous video, V is equal to V, the magnitude of V, which is ds over dt, or the algebraic value of V, which is ds over dt, times ut. Since ut is the tangential unit vector that has always the particle's motion direction. But I know, guys, that ut is not fixed with respect to time. It's variable. Why is it variable? Not because its magnitude is changing, since this is a unit vector that has always a magnitude of 1, but because its direction is changing. Let's take this case. At this point, this is the tangential direction to the curve. At this point, this is the tangential direction to the curve. So since, guys, its direction is changing, then I cannot skip the derivative of this ut, or its derivative is not equal to 0 with respect to time. And as I know, guys, if I want to do the derivative of the product of two variables, what I have to do is to make the derivative of the first one times the second variable, and then plus the derivative of the second variable times the first variable. From here, guys, comes the equation of acceleration. So you're gonna see, guys, that an acceleration in curvilinear motion using normal and tangential directions or components, an acceleration has two components, unlike the velocity that has only one component in tangential direction. The acceleration has two components. The first one is in direction of at, or is in the tangential direction, and it's called at. And the second one is in the normal direction, and it's called an. So how can I directly guess that this one is in the normal direction? Because in fact, guys, I know that the derivative of any vector is orthogonal to this vector. So it is perpendicular to the tangential ut, or to the tangential direction, and that's why it has to be in the direction of un. Let's now find what is the value of an, or what is the magnitude of the normal direction, of the normal acceleration, by finding out what is v ut dot. So guys, v ut dot is v d ut over dt. I'm gonna start by finding out what is dut. Of course, dut, it is a vector, right? Knowing that the derivative of a vector has always the normal direction to this vector, which means it has a direction of un, since un is perpendicular to ut. Now, what is dut? In order to find out what is the dut, let's take a look on this figure. This is the center of curvature. This is a position at a time t. This is a position at a time t plus del dt plus a very small interval of time. In this case, the displacement will be ds. It's a very small displacement. And I can consider that the radius of curvature is almost constant. So it's not going to change in a very huge way, because this is a very small displacement. So I can say that I am still in the same circle that fits this curve. So I'm going to assume that it has the same radius of curvature. Now I know, guys, that ut, which is the tangential unit vector to this point here, or to the curve at this point here, is perpendicular to un at this point. and that ut prime at time t prime is always perpendicular also to un prime. And this means, guys, that since un and un prime, they have an angle of d theta because I have a small ds, then ut and ut prime, they must also have the same angle d theta. So this d theta should be equal to this d theta, two perpendicular lines. Alright, so if I now start by this figure, what is the tangent of d theta? You can say what is d theta directly, because in fact, if an angle is very small, I can say that tangent of this angle is equal to the angle itself, alright? Now, what is the tangent of d theta or d theta? Tangent of d theta is equal to dut over ut in the direction tangent of d theta is dut over ut. لا لحظة tangent of d theta over ut. Now, what is the tangent of d theta in the first figure? Tangent of d theta in the first figure is ds over rho. And since I have the same d theta, then this means, guys, that dut over ut is equal to ds over rho. And you can, guys, also get this ratio from equal triangles, all right? So dut over ut should be equal to ds over rho. And this means, guys, that dut is equal to ut. Now, what is ut? It's 1. So, guys, here I'm talking about the algebraic values, all right? Because I'm finding tangent d theta, which is not a vector. So ut is 1. So it is 1 times ds over rho. So let's now substitute this dut in the equation of an here. I know that an is equal to, in vector form, v dut over dt. And I know, guys, that dut must have the direction of un, because this is the derivative of ut. And I know, guys, from vectors that a derivative of a vector has the direction normal to this vector. Since here the direction is tangential, then dut has the direction of normal. Alright? So I'm gonna, guys, substitute dut in algebraic form by ds over rho. So v times ds over rho, and don't forget, guys, dt. In what direction? In the direction of un. Alright? And this means, guys, that un is equal to, that an, the normal acceleration, is equal to v over rho ds over dt un. Now, what is ds over dt? This is also v. And this means, guys, that an is equal to v squared over rho un. From here, guys, comes the equation of the normal acceleration. So in summary, A, the acceleration of this curvilinear motion, is equal to v dot ut, and this is the component in tangential direction, plus v squared over rho un, and this is the component in normal direction. Now, of course, guys, I can find a by doing the radical of at squared plus an squared. And guys, if I take some special cases, what if rho goes to infinity? If rho goes to infinity means this is a straight line. There is no curve. Rho goes to infinity, then this is a straight line. I cannot make this straight line a curve, all right? So a straight line means rho goes to infinity, means an is equal to 0, means I only have the tangential direction, and this is what I did in the rectilinear motion in the first part of this chapter. If the particle moves along a curve at a constant speed, then this at should be equal to 0, and this an will be equal to v squared over rho. Because in fact, guys, the tangential acceleration stands for what? It stands for the variation of velocity in magnitude, while the normal acceleration stands for what? For the change in direction, guys, of this velocity. Alright? Now, if at is constant, I can apply the equations of uniformly accelerated motion in tangential direction. So in this case, s will be equal to half at squared plus v0t plus s0. V will be equal to at t plus v0, and v squared is equal to v squared 0 plus 2at s minus s0. Now, what about the radius of curvature? If I have the equation of y in terms of x, I can find directly the radius of curvature using this equation. So rho will be equal to, the numerator will be 1 plus dy over dx squared to the power 3 over 2 over the magnitude of d squared y over dx squared. Now guys, what if I have a three-dimensional motion? In this case, guys, I have to add another unit vector, which is ub, and this ub will be perpendicular to the plane formed by the normal and tangential direction, and this plane is called the oscillating plane. And this ub in this direction, guys, I will not have any motion, and that's why, guys, there is no motion in this direction, so there is no velocity or acceleration in the binormal direction. Guys, the last part of this video lecture in curvilinear motion will be about how to express also my kinematics variables using the cylindrical components. I'm going to start first by the 2D case, which is called the polar coordinate system. In this 2D case, guys, I only have two unit vectors, ur and u theta. ur will be in the same direction as r. R is the position vector, so it is from the origin into r, so it extends outward from the fixed origin O, and u theta that is perpendicular to this ur, and make sure, guys, that this theta is measured counterclockwise from the horizontal direction. And then you can use the chain rule to do the derivation of a v and a in order to find what are the kinematics variables of the polar components. And if I need to take the 3D case, as I did in the binormal direction for the tangential and normal direction, here I have to add z, uz. So I'm going to have three unit vectors, ur, u theta, and uz, and then you can derive the velocity and acceleration knowing that the position will be rur plus zuz, and you can find the velocity and acceleration. I want you guys to do it by yourself. You have to derive the velocity, you have to derive the acceleration, and you have to show me how, as I did for the normal and tangential directions. And you have to record a small video, not more than 5 minutes, explaining how you can find Vp, Ap by using the chain rule and by deriving the position in cylindrical coordinates. Thank you.